What we're looking at here is joint time frequency. So it's one of those things that it's not what you really want to hear straight after lunch. But I had a look at it and I thought, well, can I take out all of the maths on this one and take out everything that's not really necessary and just put it in pictures? So hopefully I've managed to achieve that. So there's no maths, and the consequence is it's shorter than the half an hour. So let's have a look at it then. So first of all, it's joint time frequency. So what is frequency analysis? Well, I'm not going to go into any maths. So frequency analysis looks like a prism. When we see light, we see colours, blue, yellow, red. And if, of course, you're a lady, then you also see magenta and various colours that men just don't see. You know, we see blue, red and green, really. And yellow, well, that's just, well, it's just pale red. So, but what happens is we see these colours, and what they are, they're a mixture of different wavelengths of light. And a prism is able to separate them again. So we shine a light, which we see as the sun coming in as yellow. It goes through the prism, and what we actually see is it separates those wavelengths. And each wavelength is really a frequency. So what a prism is it's nature's frequency analysis tool. And what we use instead of that is, there we go, so that splits up all the colours, and that's essentially what we use as a Fourier Transform. So a Fourier takes a waveform and separates it and pulls out all the different sinusoidal tones, and it tells you usually what the amplitude and frequency of those are. Okay, if we went into maths, we'd also find there's a phase in there, but we're not getting into that bit today. So it's really to plot that amplitude versus frequency. So what is joint time frequency then? Well, let's have a little look at a block of time first and look at how frequency is calculated. Then we'll see about joint time frequency. So in order to calculate frequency content, you can't do it with just one point in time. You've got to have a series of points, because frequency all depends on effectively the differentials, the change of gradients and things. So you need to have a buffer. And if we see a buffer of time, which is, say, delta t seconds long, there's a few other attributes we can give it. We know, for example, if it's digitized, we can actually work out what the sample rate was, so how many points per second. We can look at the total number of points in the buffer, so delta t seconds has n points. And at any point in t, we know its amplitude. We can just measure its amplitude. We could also do some more advanced statistics. So the root mean squared of a time history is actually, if we take each of the points, we square it to make it positive, add them all together, divided by the number, and then square root it, it's the RMS of a signal. So where does all of that live when we look at a PSD? What are the statistics of a PSD? Well, here's our PSD that's gone through our mathematical prism. The first 2 points are quite simple. The first one is the first frequency point is at 0 hertz. The maximum frequency here is the Nyquist frequency, so that's set at half of the sample rate. Another interesting statistic is the frequency resolution, so delta f, is actually equal to the sample rate divided by the number of points in a buffer. So if you wanted to have a higher resolution, so make delta f smaller, then you can either increase the number of points you're looking at, so increase your buffer size, that gives you better frequency resolution, or just downsample it. Sounds a bit strange, but downsampling reduces the Nyquist. How about the RMS then? Well, this is the nice thing about PSDs. They're normalized, so the area under the PSD is the mean squared. So if you take the area under a PSD and square root it, that's your RMS. And that's the way that we can always tell that we've got the answer right with a PSD. It's the IEEE standard. So we've always got an acid test of what the PSD is telling us. So when we do joint time frequency, what do we do then? Well, we simply take buffers of time and we work out the PSDs and we plot them. So it really is that simple. There's one little quirk though that comes in. So as I say, you can't find the exact frequency content at one point in time. You can only find it out of a buffer because you need several points. And this little point is quite interesting, because if I wanted to increase the resolution of frequencies, I need a bigger time buffer. But if I've got a bigger time buffer, I may miss some peculiarities at a set time. So if my time buffer is 10 seconds long and I had an event occurred, a bump at 1 second in, I would just average it, I'd miss it out. So if I want to increase my resolution in time to get all of these little 1 second blips in there, I'd have to reduce the buffer size, but the consequence of that is my frequency resolution reduces. So delta F increases. And this is really, it's the Heisenberg principle, the uncertainty principle. You can measure something's position in time, or you can measure its frequency, but you can't actually simultaneously get good accuracy in both. And we call this the Heisenberg cell, and it's of constant area. So if you want to increase the time resolution and make that smaller, the net consequence is the frequency goes up. The area is always the same. You can't play with that. Now, a lot of people say, well, I'll just change the sample rate. That doesn't work either, because all that does is actually increase the Nyquist frequency bit, so you still end up with exactly the same problem. So this is one of the consequences that we have in joint time frequency. So if you look at some of the textbooks that go beyond what we're doing here, you'll see a lot of it's trying to deal with this insolvable resolution. How can I improve both time and frequency resolution simultaneously? And lots of people have looked at that. So you've got people like Choi Williams and things like that. They're all ways of doing it. But we all know that in real life you don't get, you can't get something for nothing. And it's always at a sacrifice. So if we look at things like scalograms, like Choi Williams, Vigneviel and things like that, the penalty you pay is phantom signals. And the problem with the phantom signals is you can't tell what's real and what's the phantom one. So really it doesn't help us. You may have also come across wavelets. Now wavelets, there's two types of wavelet broadly. There's what we call orthogonal wavelets, which you can go into the wavelet domain and then come out again, a bit like Fourier. And there's things called non-orthogonal wavelets or continuous wavelets. And they're what we tend to use for joint time frequency. But you don't get something for nothing. The way wavelets work is for low frequencies, you get a long wavelet which takes a long period of time, and then as the frequency increases you decrease the size of your wavelet as well, so it becomes more localized in time. I'm just going to move out a projector shot. You'll not like this, but so essentially at the low frequencies we start off with a big buffer. As we move up frequencies the buffer actually gets smaller, so usually it goes in exponential blocks. So the first buffer is that length, then you get 2, then 4, 8, 16 and so on, gradually splitting it up. So the wavelets is really neat, but remember you don't get something for nothing. The problem is the scale doesn't really mean very much. So you'll get a nice picture to show you what's going on, but you can't just measure the volume under it and find out that it's the RMS, for instance. So it becomes hard to interpret numerically. It's a nice pretty picture, hard to interpret. And that's really why we stick to this type of approach, because in engineering terms it gives you a nice picture, but it also allows you to take numerical results and use those in calculations. Now again, when you're looking through the books, you've got to remember that people have spent a long time doing this and they've written a lot of papers, and most of those papers are written to impress rather than to inform. So they've come up with new terminology. So one that you'll see, and the one that we tend to use, is actually called a Gabor Transform. But it's just a simple transformation that we've done here using a windowing function, which is actually of a Gaussian signal. So we'll look at that in a second. So this is the main thing. This is the bit that we spend a lot of time on, trying to reconcile this joint time and frequency. But in reality, you're stuck with it. So you want high frequency, you've got a big long buffer, and you'll miss little bits in between. You want good time resolution, you're not going to get good frequency resolution. Okay, so this windowing function and this Gabor transform, what is it? Well, let's say that I've just got one buffer and I've just got a sine wave in it. So when we look at its frequency spectrum, we'd expect it to be one spike. This one, if this is a second long, must apologise to Kurt again for walking away. I've got sort of about 4.8 cycles in here, but that one's cut short. Now, Fourier works by trying to fit sine waves into a signal. And it can't quite fit all those sine waves in, because how does it jump from there back to zero? So what Fourier looks like is it's trying to assume that that is one continuous signal repeating over and over again. And in order to get it to jump from there up to there, it puts in these freak harmonics. And we call that spectral leakage. So when we analyse this incomplete sine wave, because of its jump, that spike, it will have to add in those extra leakage functions in order to make that work. So how do we get rid of this spectral leakage? Because that's an artifact of the analysis. It's not part of the signal. And the way we do it is we employ a windowing function. We force the signal to start and end at zero so we don't get big jumps to give us this big problem. So now, if we take our sine wave here and we multiply it by a function, which these are always similar, they always have 1 in the middle and they're always 0 at the ends. But what this means is when we multiply it, we force it to end at 0 without a big jump. So in this case, if I analysed it, what I'd get is I'd still get some spectral leakage occurring down here, but it's a lot more confined than it was. And also you'll notice it's asymmetric too. So if you were to actually calculate the centroidal frequency, it now comes out at 4.8. And the fact that we've taken this windowing function, we can actually calculate, we know the ratio of area under it to the total area of the buffer, so we can add back that frequency content as well, assuming it was uniform. So by using a windowing function, it enables us to avoid this spectral leakage so we can come up with a more defined and accurate answer. Now this is a bit of a problem though, because although we've made it nice and clean and without spectral leakage, what happens when we do joint time frequency? Well, you run the potential of multiplying vast amounts of your signal by 0. So if something interesting were to happen here, you'll never notice it because the windowing functions have zeroed it. So what we do instead is we overlap the buffers. So here we go. By default, we use a 67% overlap. So each buffer overlaps the previous by 67%. And then we end up with like the three-phase electricity thing, where the net result is we've sampled everything with a uniform rate. So we analyse this one, and we can produce then a spectrum. We analyse this one and produce a spectrum. It actually looks like we've got spectrums which are closer in time now. We've still not destroyed Heisenberg's principle. That still applies. We can't get rid of that. But it has enabled us to get a better time resolution, and simultaneously we're addressing these problems that we've got of the buffer wraparound. So that windowing function, you'll see quite a few. The most popular one that we use in most analysis is a Hanning window. The Gabor transform actually uses the windowing function, which is the Gaussian, the bell-shaped curve. And that's the only difference. So if you're looking through the books and you see the Gabor transform and short time frequency analysis, it's the normal frequency analysis we used to, but using that bell-shaped curve instead of the Hanning window. So that's pretty much all there is to it. What's it look like in the glyph? Well, we've got a new glyph. When did it come out? It came out a bit ago actually. It was about version 7 or 8, this one. What it's doing is that for each point in time it's showing you a spectrum. So we've got time running this way and we've got frequency running this way. And what this is actually showing us is the frequency content in terms of colour as we're actually for each point in time. Now very often when we plot this, we plot it in a way so that we see the joint time frequency and we also see the sine curve, the time history running underneath. That enables us to try and find, when we see interesting artifacts occurring here, we can reference them back to what was happening in the time domain as well. And the other thing we usually show is twisted to one side, we usually show the PSD as well. So this is the instantaneous frequency content. This is showing us the average content over the whole period of time. And we can do that within our software using the Studio glyph. So you can plot one thing or several, or in Studio we can pull them all together to make the joint time frequency glyph. If we have a look, then there's not many properties in this. The main one is the method, which is short time frequency, where you can specify your windowing function, or if you just choose the Gabor transform, it chooses that Gaussian bell-shaped curve. The other thing that you want to do is to tell it how long the buffer is that you use. Remember, bigger buffers give you a tighter frequency resolution, but they're lower in time resolution. So you may not be going for 1024 points. If you want better time resolution, you may be going for smaller buffers. The other thing that you look at is the overlapping of them. So how do they increment? So in this case, we're incrementing by 67% overlap to be able to get the plot. So it's a very easy thing to fill in, and the nice thing is it's a very fast calculation as well. You do have the option, rather than percentage, again, if you read the textbooks, what they do is they calculate this for every point in time. Now that's very good if all you're doing is analysing very small signals, but if you're analysing a car going over a road, that's a lot of data that you're analysing there. So that's why we prefer generally the percentage overlap. But that is a difference that you'll see in the textbooks, because scientists only deal with little bits of data and we've got oodles of the stuff. Now, there's another type of joint time frequency which we use quite a lot. Rather than having a time axis, very often we want to relate it to something other than time. For example, a ramped engine test, we want to reference it to the RPM. So in this case, we're measuring two signals. We're measuring the engine speed here, so we know time and we know engine speed, and we're also measuring, say, a vibration signal coming out of the engine. And what we want to do is to look again at the joint time frequency, but this time, rather than time, we want to reference it to the RPM. So how does this work? So we start off with the two signals, and basically the user chooses a range of RPMs that they want to look at. They don't have to pick them out manually. You can just say, I want to start at this number and go to this number with 50 steps. And what it then does is for each RPM, it goes to it, finds the time, takes out that time buffer there, and then it centralizes the analysis on those points. So here, what I've told it to do is to have these buffers. So there are 6 buffers with a 67% overlap. So it finds the middle and then goes either side of it and overlaps and does everything else with reference to that point that you've selected. So what's the difference here? Well, the difference is sometimes you can be reanalyzing the same area of data. So when I did it, if I chose that my previous data point was down here, then there may have been overlap between those. So I'm actually including the same data in 2 parts. The other one may be that if my resolution of engine speed is very coarse, I may miss lots of data out. But the whole idea is to try and get this plot of vibration at a particular engine speed. So when we look at it, we get a plot similar to that. Now this is characterized by these order lines. So this is a ramped engine test. This is now engine speed, and this is frequency, and this is the PSD coming out. And what we can see are these are multiples of the rotation speed of the engine. And usually we could start to look at this. So for example, if I drew an order line on there in our display, and that came out as being the second order, so these frequencies are twice as high as the engine frequency, that's probably telling me that's a 4-cylinder engine, because there are 2 firings with every rotation, so I see a dominant second order. And we've got all sorts of software in there that we can pull out those lines, we can start to look at them and analyze them. But signature analysis like this, or waterfall analysis, is just a type of joint time frequency analysis. That's all, really. Okay. Another type that, so this is new in version 10, is the ability to have a joint time version of the frequency response function. So what's a frequency response function? Well, if you measured 2 time histories from 2 points in a structure, one might be input and the other output, or they could just be 2 signals, then the frequency response function is actually the relationship between the two. And very often we can do gain and phase. This is a gain plot, and this is showing that the ratio from this to this, for certain frequencies, this is much higher. It's got a positive gain. And the frequency response analysis glyph calculates that. Well, there's a new feature in 10 which now allows us to actually look at that with time. So here we go. If we now switch it into waterfall plot, rather than just averaging it and producing an average frequency response, it produces a frequency response at all points in time. And what we're seeing here is that at some point there's been a change in structural response. So the relationship between the two signals has now changed. And we could see that really dramatically here, but if you look at these two plots, you can't suddenly see it very clearly. And we use this feature for quite a few things. One of its main uses is for diagnosing problems in structures. So if a structure starts to crack with early signs of fatigue, very often you can spot that by changes in its stiffness and therefore changes in its transfer function. So this will enable us to do that type of check. It's also very useful for things which are non-linear. So we're always used to things, you know, when we vibrate something at a level, we see the natural frequencies. But if they're non-linear with rubber and things like that, if you increase the amplitude, then the frequencies can change as well. Very often they reduce with that. And again, this glyph will help us to analyze those non-linear materials and their response, so we can start to see whether or not we need to be considering them. So in conclusion then, when we're looking at joint time frequency, then really it's how frequency changes with respect to time. Rather than a single PSD, we calculate the PSD over several points in time. With waterfall analysis, this is a special kind of joint time frequency which is correlated to another parameter, and mostly that's going to be engine speed for us. And finally, in version 10, we've also included frequency response analysis, where now rather than just getting one FRF, we can see the FRF with respect to time, and that enables us to start to see nonlinearities or changes in the structure's response. Okay.